mixture. For those in Zoom, we will have only 5 minutes break between the lectures. I continue today with monoidal categories, and we'll finish this, and then on Thursday I will talk about modular categories. So first is a small addition to which therefore has a special number. If C is semi-simple and abelian, and X is an object which is simple and rigid, and then also XV, the right dual, and VX, the left dual, are simple. And as a consequence of that, the functor, right duality or analogously left duality, defines a permutation on the set of isomorphistic classes of simple objects, which we call lambda. And I denote this permutation by putting a bar on the label. So that means that the simple object, the representative of the class lambda bar, is isomorphic to the dual of the representative of the. There is no preferred isomorphism, and that actually plays a role for something we will do later. Next is a lemma. If C is rigid, then the double dual functor, say right dual, all the statements are analogously valid for left dual. So this is an ender functor of C. This comes with the structure of a monoidal functor. And to prove this, the one possibility is to first invoke lemma 269, which says that we can always choose the duality such that the dual of 1 is equal rather than isomorphic, just isomorphic to 1, and that the dual of X tensor Y is the same as Y dual tensor X dual. And if you make this choice, then this is easy to see. Then you have to check that if you have any other choice by using that this is equivalent to then it's still valid. Now, when you have that, then it's a natural idea to ask what can it happen that this double dual actually is the identity? This doesn't really make sense. You should say it's isomorphic to the identity, and because they are both monoidal functors, it should be monoidally isomorphic. And this is an interesting situation. And then you define a pivotal structure or pivotal on a rigid monoidal category C. This is a monoidal natural isomorphism. From the identity functor to the double dual functor. And this is often denoted by pi. And then a pivotal category is a rigid category C with the choice or datum of pivotal structure. And this is structure. So for a given monoidal a rigid category, there need not exist a pivotal structure, and if there exists, there can exist several different ones. And we will see one very simple example below. In the graphical calculus, I will denote a pivotal component pi x of pivotal structure, so this isomorphism from x to x double dual by a symbol like that. And then a remark. If we use lemma 270, then we see that for a pivotal category, we always have that the left dual, as functors, the left dual is isomorphic to the right dual. And in fact, as monoidal functors. As I should not write this as op-monoidal functors. Well, it depends on how you. So yeah, maybe I can write it. If this is, if you think of this as functors from C to C opposite, and not as contravariant functors from C itself. Yeah, maybe I write it. And so this is actually equivalent. If we have such a monoidal isomorphism, then we get a pivotal structure also. And this has been called a sovereign structure. And in the older literature, I would say this is used rather often, but nowadays since it's equivalent, there's no need for a separate notation. Then this one here. You can, well, this I could have presented a bit earlier actually. You can ask how do evaluations and co-evaluations be together with the duality. So what is the dual of say the evaluation on X? And you can see this is the same as the co-evaluation on the dual of X. And how do you prove this? Well, this is the evaluation. We have X here. The dual, by definition, using this choice we made on dual for a tensor product looks like this. But now here you can use the snake identity. So this is the same as this. But now you have to be careful. Here we have X dual. So here is X double dual, and therefore this here is really you see X double dual. So this is the same as what we have as the co-evaluation for the dual of X, and analogously you can easily see this in the same way. The co-evaluation, the dual of the co-evaluation is the evaluation for the dual. And from this it follows in particular that a double dual of the evaluation is the evaluation of the double dual object, and analogously for the co-evaluation. And once you have this, you can ask what does it imply for the duals of the components of the pivotal structure. Maybe I take this away to use the space here. So what you see is that the dual of pi x is the same as the inverse of the component for the dual of x, and then in particular the double dual of pi x is the same as pi for x double dual. And how do you see this? Well, if we want to show that we have this equality, we can compose this morphism and this morphism, and have to show that it's the identity in two possible ways. I show one of them. So if we take pi x, then pi x dual is this morphism. Then I have here pi x dual. And you can check that I can compose them in this way. I don't write the labels for the lines. They follow from what we have here. But this is the same thing as just bringing this a bit up. And now you see here, if you look at this part and use this choice we have made for the use that this is a monoidal natural transformation, then this is the same as pi x, is it x dual tensor x. And now we can use that this is a natural transformation. Here we go to the invisible unit object, so we can bring this up. And then we see that what we get is, let me draw it just like that. So here we have the evaluation on here. Sorry, here we have. Yeah, let me write it like that first. X dual tensor x, and here we have the evaluation on x, and then we bring this up, meaning that we have here the evaluation of x, and then here we have pi of 1, but pi of 1 is just the identity, so this we can remove, and then the evaluation that we write out again in this form, and then use the snake identity and the identity morphism. And another comment is that if we now look at this result here, then if C is in addition pivotal, then it follows that this permutation is an involution. So doing it twice gives the identity. And it's not only if, in principle, it can happen by chance that we have this, but being pivotal is the only systematic reason for this being an involution. Then a side remark concerning vector spaces. Let V be a vector space, and I indicate here that it might be infinite dimensional, arbitrary vector space. Then we have a linear map. Let me call it IV from V to its double dual. But this is just an algebraic double dual of vector spaces. This is a linear map which we can define by IV applied to a vector V in V. We define this by saying how it acts on an element in the dual vector space. And it acts just by evaluation. And this indeed gives a natural transformation from the identity functor on the category of all vector spaces over K to the double dual in vector spaces. And an exercise would be show that when restricted to vect Okay, so by this with small v, remember I mean finite dimensional, this gives a pivotal structure. And remember that we do have duals in the sense of vector spaces, also for infinite dimensional vector spaces, but they do not give us a duality, a rigid duality on the category. Then important result which simplifies many arguments, which is analogous to the strictification result for monoidal categories. Every pivotal monoidal category is pivotal monoidal is equivalent as a pivotal monoidal category to a strict pivotal category where strict simply means that I is equal to the identity functor. Not pi. Pi is the identity, double dual is equal to the identity. And then short example which shows in particular that pivotal structure is indeed structure. We can look at the category of supervector spaces. Finite dimensional ones, which I do not write. Okay, well, when I say supervector spaces, at this point, they are just set two graded vector spaces because we have not talked about grading yet. And but let me use this terminology. Anyhow, what do we? This is a semi-simple category which has two simple objects which are as vector space. It's K. There is a well. Let me write it like that: K10 and K01. This is the tensor unit. So on the tensor unit, the pivotal structure has to be the identity morphism, but this is hard to read. Here we can, if you use that pi has to be monoidal, you see that there are two possibilities for for this component, namely plus or minus the identity on this object. And in the first case, actually, with plus, you get a unitary category, unitary monoidal category, and another one not. But there are some people like Ingo who prefer the other one. Now, this also has consequences for the dimensions of these objects, but those I have not yet talked about. And the reason for that is that we need pivotality in order to define that. So if we have a pivotal category, then we can make the following definitions. So see pivotal category with pivotal structure pi. Then for an endomorphism F, say in XX, one defines, let's move yellow, continue with white, trace R of F to be some combination here, which I do not write as formula, because it's nicer to write it, to draw it, and analogously trace L of F. Similar formula. This is called the right trace, and this is called the left trace of the morphism F. And graphically, this is as follows: the right trace. So we take F, and then we use may just use the right duality. We could also use the left duality, but that's equivalent. So we have X double dual, X dual here. We use again a right duality, meaning that here we have X double dual, and then you see in order to get to here to X, we can take the inverse of the component pi X. And so this is a morphism, endomorphism of 1. And analogously here, we do this we trace on the other side. In that case, we have X here, so X dual here, therefore X double dual here. And that means we need the pivotal structure on X here. And in general, these are two different morphisms. We also now say that the dimension, the right or left dimension of an object X is by definition the right, respectively left trace of the identity morphism on X. And very often, for us, almost all the time, we are in the situation that we have a C linear category and the monoidal unit linear simple. In this case, we can identify this morphism space just with the ground field K. And concretely, there is a unique isomorphism from this morphism space to K, which is actually an isomorphism of unitary associative algebra. K. Now, something I don't write down. Okay, no. Is no, maybe I do it, is that we explicitly use the pivotal structure here. So in principle, one should add in the notation that we have a certain pivotal structure. Since pivotal structure is structure, this means that these quantities, trace and dimension, are not defined for the category C, but for the category C together with the chosen pivotal structure. Trace and remark. And on the choice of pivotal structure. And example, in this case here, we get the dimension of this odd unit, as it is called, is plus or minus 1. And some people like to say for super vector space, for the odd one-dimensional super vector space, the dimension should be minus 1. It's then called a super dimension. So actually, if you look in the not category related physics literature, and use of super dimension is the usual thing. But if you look in more detail what is usually done with it, it's not really relevant that you have chosen this pivotal structure. You could also choose the other one. Then some properties. Lemma or remark or exercise to prove is the following: traces are cyclic. So a trace of G after F. Assume F and G are composable in both directions. So F, say, goes from X to Y and G from Y to X. And this is the same as trace F after G, both for the left and for the right trace. Then left and right trace are related in the following way. If I take the right dual of morphism F, and this is the same as the left dual, the trace of the right dual is the same as the right trace of the right dual is the same as the left dual. The left trace of the morphism F itself. So in particular, this means that the dimension, right or left, of an object X is equal to the dimension left or right of its dual. And something I haven't written here, which however is also important, is that the dimension of X equals the dimension of Y if X and Y are isomorphic. Meaning in particular that if X is not trace dimension. If X is self-dual, so isomorphic to its dual, then its left and right dimension are equal. And finally, if C is scalinear and 1 is linear simple, then we have the trace left or right of the tensor product of morphisms is the product as numbers in K of the individual traces. Then let me mention that one can define dimensions, or one does. In fact, the Ettinger et al. Book does it, define dimensions also for categories that are not, or traces for categories which are not pivotal. In that case, you do not define a trace for an endomorphism, but define a trace for morphisms from X to X double dual, respectively, when you take the other trace from X double dual to X by simply omitting the pivotal structure here. And we might at first think that this is then not of interest, assuming that this here is of interest, which it is, but there are situations where it indeed makes sense to use this definition. And then I should add that there are various other types of traces which can be considered, which are not close, but somewhat similar. But there are even situations where with one notion of trace, with one notion of trace, the dimension of a certain object is 0, whereas with another notion of trace, it's non-zero. Now, it's a bit annoying that we have left and right traces and dimensions, but there is a class of categories where they are equal, and they are introduced as follows. We say a spherical structure on a rigid category C. This is a pivotal structure such that the left and right traces are equal. In fact, it can be shown that this is equivalent to that the left and right dimensions are equal. That's already enough. Of course, it follows from that, but also it goes in the other direction. And if you call this spherical structure, but for a given pivotal structure, being spherical or not is a property. A given pivotal structure is either spherical or not. There are no choices. Then what about this?
The pivotal category is equivalent to a strict category. It's good. Spherical category equivalent to a strict spherical category.
It can happen that you have two on the same rigid category. You have two different pivotal structures. One of them is spherical and the other not. According to the theorem, both of those pivotal categories are equivalent as pivotal categories to a strict one. But it's similar like with the stratification theorem for monoidal categories, that somehow the strictified category that you get still remembers where it comes from. And for that, you have to look at the construction of the strict defined version. You cannot just say that I take this category and put the pivotal structure to the identity, but rather there is a strictly pivotal category which is equivalent, but that is has different objects. So you and the concrete construction is in fact somewhat similar to the construction in the monoidal case. So if I remember correctly, you define the objects of the strict defined version as sequences of objects in the origin. Then briefly about the origin of the terminology. If you think of such a graph not drawn on the canvas that we are usually using, but the canvas that is spherical, then if you look from the other side of the category of the room, from the corridor on the sphere, the two pictures, left and right is within. And according to that, actually, for spherical categories, the ordinary graphical calculus, which I'm otherwise always using for monoidal categories, which has the plane or a rectangle as canvas, is not optimal, but there is a version where we can use circular coupons. So for a coupon like here, it's clear according to my conventions what is on the bottom is the domain, and what is on the top is the codomain. In this case, here now we can just have arbitrary lines which can be incoming or outgoing, and this could correspond to one particular morphism in this description, but also it's you could choose one where you instead look at starting from here, take two dualities together the pivot structure, and then in fact one way to define this is via a suitable limit of such graphs. And this is the formalism, the graphical calculus that is best adapted to string and norms. Then another quantity that is of interest is the following. Let's assume C is pivotal, and the pivotal structure is called I as usual, and C is in addition semi-simple and abelian. Then we can look at the following morphism, where I use the ordinary graphical calculus. We need the following. So we take y lambda. So this is one of the representatives of this isomorphism class, representative of the isomorphism class of simple objects. Here we take the inverse of pi y lambda. I was actually not what I like that. And here I have a morphism which I call sigma lambda bar. And here I have sigma lambda inverse, where I have chosen for each morphism space y lambda to y lambda bar dual. Remember, they are isomorphic and they are simple. So they, and I assume actually one is absolute linear simple, and they are one-dimensional. And I make it some choice here, some arbitrary choice, and then with what I have written here, you can reconstruct what the various objects are. So starting from here, and you see you end up with the same object. And so then you see by construction that this is in fact some number, nu lambda, non-zero number times the identity on y lambda. And furthermore, one can show by direct calculation composing this with the analogous morphism for lambda bar and using some intermediate morphisms that we can compose them, that this number nu lambda times nu lambda bar times the trace, right trace of the pivotal structure for y lambda is the same as the left trace for the inverse of the pivotal structure for y lambda bar that you do directly, and then using these results for duals of pivotal structures, this actually implies that nu lambda and nu lambda bar is equal to 1. And then there are two possibilities. If lambda is equal to lambda bar, so the object y lambda is isomorphic to its dual, then nu lambda squared has to be 1. So nu lambda has to be plus minus 1. And if lambda is not equal to lambda bar, then you see here we have sigma lambda, here sigma lambda bar. So this depends on the choice of lambda, and one can see that one can choose these sigma lambdas in such a way that nu lambda, in this case, always is equal to 1. And this number that you get here is called the Frobenius-Schur indicator. And in the particular case that the category is the representation category, so in complex vector spaces of a group, this gives back the classical notion of Frobenius-Schur. And finally, over time, but let me add this here. The dimension left or right is the same in case A of y lambda. Can be shown. So this is the pivotal dimension, remember, is equal to nu lambda divided by one particular 6J symbol, which is the lambda bar. So this actually is one of those 6J symbols which are H independent. So this is fixed, but depending on the, 6 J, 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 6 pivotal structure, you can have different values here. And over time, so let's stop here and then maybe we continue in 5 minutes from now. Now come to section 7, which is about more string calculus, which I will introduce with the help of BI and Hopf algebras. And there are various things about Hopf algebras I want to tell you, but if time does not is not sufficient, I will leave out some of them. So the first thing to observe here is that we have talked about algebras in non-invertible categories. Natural question is what about commutative algebras? And for that, we first talk about the vector space case. We know what it is. So now C is vector spaces, and then we define what I call the flip map. There are other names for it. Tau from the tensor product of two vector spaces V and W to the tensor product in the opposite order, which simply interchanges the two elements in for an element here that is of this particular form, and then continued by familiarity. And then you define the opposite algebra to an algebra A mu eta to be A mu opposite eta, where mu opposite is the multiplication of A after I should here write here tau VW after the flip of A with itself, and graphically I would draw this as follows. If I have the ordinate multiplication mu here, then I draw it like that. Now, in principle, you could say that there are good reasons to say one should not have here over and under because it has no meaning. But when I see something like that, I find it hard to distinguish it from this. So I prefer, even in this situation where over and under does not play any role, to draw it like that, so that it's somehow is immediately seen that there is a thing. But in this situation here, I could also draw it like that. And analogously, one defines the co-opposite co-algebra, where for the co-opposite co-product, one has analogously the co-product followed by this flip map. And just as an example, if you don't write down, if you and then we say A is commutative if and only if, I can write mu op equals mu, so the opposite algebra is equal to the algebra itself. And analogously for co-commutative, then when we talk about co-algebras. And as an example, if you take if you take any set, then the vector space generated by S is automatically co-algebra and in fact co-commutative. If S is a group, then K of G is also an algebra and is commutative if and only if the group is abelian. And another important example in various applications is that the universal enveloping algebra of an arbitrary algebra is a co-commutative. Now, there are two interesting ways of combining algebra and co-algebra structure, and one of them I introduce now, the other one I will introduce on tomorrow. So we say a bi-algebra in K for now. We are still in is quintuple consisting of a vector space and morphism Q, eta, delta, epsilon, such that here we have an algebra. Here, together with A, we have a co-algebra, and delta and epsilon are morphisms of algebras. In order for this to make sense, I have to use an algebra structure on A tensor A and an algebra structure on K. On K it's trivial, we just use the identity. On A tensor A, the algebra structure is as follows. We start with 2 copies of A, 4 copies, and end up with 2 copies, and you use the product. 2 copies, and here we have the flip map of A, which as I said, will usually draw in this way. And then we could write this in formulas, but it's easier to do it graphically. That delta is a morphism of algebras, then means that we have this equality, where here I have the flip map, and this equality, and that epsilon is a morphism of algebras. Says that co-product after unit is unit tensor unit, and unit co-unit after unit is the let me write it, the identity on the tensor unit, which is K, so it's the number 1. And indeed, an example, if you take the group algebra K of G, then this is a bi-algebra with this co-product that I have indicated. Now, we have seen in example 188, for example, that for bimodules of an algebra, we have a tensor product. And in particular, if the algebra is commutative, this gives us a tensor product of modules. However, if you have a bialgebra and the object we get as a tensor product was defined by a co-equalizer, so it's a in the semi-simple case, it's just a sub-object of the tensor product over K of the underlying vector spaces. But there is also in the bialgebra case a notion of tensor products where we do not change the object. And we formulate this as a proposition. So for R bialgebra, and Mn modules, say left modules, we set A in M tensor N as A1. This is a notation that I might not have introduced. Did I introduce Theta notation? Maybe not. A is an A, M is an M, N is an N. Did I talk about Theta notation? No. Okay, so I do it later, which I should have moved here. So if we have delta of x for let me say v for any. Let's take a co-algebra C. The delta of C is an element here. So assume we are, for example, there are certain finiteness conditions, then I can write this as a sum over some coefficients, psi ij xi tensor xj, where there is some summation over ij, which I don't really have to specify for the argument here. And then often, and this is due to Sweetler and others, one writes this just as without a summation, and I can take the coefficients into these elements here. One just writes this as xi tensor xj, and I should have written it differently. I1, I, and x2i. That's the notation that I'm using then here. And then I have a single summation. And then one just writes this in the first place by leaving out the summation. And then one even leaves out the symbol I here, which of course does not make any sense, not much sense if I don't have the summation. But that simply means here I have taken the delta, the co-product of A, and then take I have a sum where in each summoned I have terms of this form. And the statement is that this endows the vector space. Let me write it explicitly with a dot here. So M would be a vector space M dot with some action. M dot tensor over K, N dot with the structure of an A module, so an object in A mod. And indeed, this extends to a functor from A mod times A mod to A mod, which provides a monoidal structure on A mod. is a monoidal structure. So we have a tensor product satisfying all the conditions. Graphically, this would correspond to the following. We have M or M dot, N dot, and then want to define the action of A on this tensor product. And we define it by taking the co-product and using the flip map here to go through this line. And then here we have row N and row M. That's what I indicated here by the dots. And it's a nice exercise to check that this is really, this gives you an action of A on this object. The natural question is, when does in such a situation the category A mod not only get the structure of a monoidal category, but even of a rigid monoidal category? And this leads to the notion of Hopf algebra. And for this we define, so for A equals, with the same notation as before, the Pi algebra, we define an antipode on A is a bilinear map. It's a k-linear map. I cannot read what often denoted by S from A to itself, such that, and here I write the requirement first as a formula, but it becomes again much clearer, I would say, if you draw this. So product after antipode tensored with identity after co-product. It's the same as unit after co-unit, and it's the same as what we get if we interchange here identity and antipode. Graphically, this says the following: if I denote the antipode by a little circle, then this says that this morphism equals this morphism equals this morphism. Another way to say this is, in general, if I have a co-algebra and algebra, then there's a notion of convolution product, and this says that the antipode is a two-sided inverse of the identity under the convolution product. Because what one has here is actually the one for the convolution product. And then one also has a different notion, which is a slight variation of that. I call it S tilde, and I only draw it if I put S tilde, which I now write as a plot on one side, on the other side, yeah, then I have this identity. So up to this is defined like the antipode. And then definition, main definition here is that the Hopf algebra is a bi-algebra together with an antipode. For example, the group algebra of defining group G is actually a Hopf algebra if we define the antipode by saying that the S on the generator corresponding to the group element G is the generator corresponding to the inverse group element. Which is yeah. Then some results. About Hopf algebras, bi and Hopf algebras. And up to this one, remember, we are always still in vector spaces, but we will soon generalize this. Remark or lemma or exercise. In general, a bi-algebra need not admit an antipode, but if it does, then it's unique. Actually, this follows directly from the interpretation of these formulas as being inverses with respect to the product. And then if S is invertible, in general it's not, then S, if an antipode S is invertible, then its inverse is a skew antipode. And also the other way around, of course. And then also, if you, since these differ by inserting suitably a flip map, it's not so surprising that H, I now use H for Hopf algebras, mainly mu, eta, delta, epsilon, S. No, that's not what I want to say, but S tilde. Let me see. Yeah, if this is a bi-algebra with skew antipode, and we can actually easily make it have an associated Hopf algebra with the same vector space, same algebra structure, but opposite coproduct. Or same vector space with opposite product. And same co-algebra structure. We can shift the place where we insert the slip map around. Mike, if H is commutative or co-commutative, when I write H, I now mean that we deal with a Hopf algebra, then the antipode squares to the identity. Also, if H is finite dimensional, I have not assumed this so far, then the antipode is invertible. And that we remark that in the infinite dimensional case, you can have Hopf algebras with non-invertible antipode, but it's not easy to find some. There is. I don't write this down, but if you want to find an example for that non-invertible antipode, is paper by Categorical, which discuss this. And finally, a real exercise. I think one should do this. Recall or look up what this convolution product precisely is. Maybe I write convolution product F in G, say linear maps from algebra A, from a co-algebra, from A to B, where A is a co-algebra and B an algebra. For example, A equals B a bi-algebra, or Hopf algebra then in our case. Then we say the convolution product is this morphism. And the first thing is show, and preferably graphically, because otherwise you have to think more. I would say that if I compose S, then compose with mu. No, nonsense. With mu, then I get the unit for the convolution product. It's easy to see. A bit more effort is needed to show that mu convolution product with mu composed with bitmap composed with S tensor S also gives this. And from this, it follows, well, which you have to show is that S composed with mu equals mu composed with bitmap composed with S tensor S. And this means that graphically, this picture saying that the antipode is an anti-algebra morphism. And it's also the same way you showed this antipode algebra morphism. And this is a property that you use. That is very useful. A side remark here for now, but I will use this a little bit on Thursday, is the notion of a Hopf pairing. Actually, it's called Hopf pairing because it's interesting for Hopf algebras, but you only need that you have an algebra that is also a co-algebra. This is a pairing, so linear map from A tensor A to the field, or a morphism from A tensor A to the tensor unit, such that if I compose it on one side with the product, then I get the same as composing it on the other side with the co-product and using it twice. And if I compose it with the unit, then I get a co-unit, and the same equalities if I flip left and right. Now, remember that I started with the question, when do we have a duality on a category of modules of bi-algebra? And the statement is that if H is a Hopf algebra, then H mod admits a duality. I should say, well, in my conventions, the right duality, independence then state will be one duality. If H is a bi-algebra with bi-algebra with skew antipode, then its category of modules admits the left module duality. And then in particular, if A is a Hopf algebra and S is invertible, then we can use both of these according to what I had said before. So that in this case, see that H mod is rigid, left and right rigid. And one can also show that in this case, the left and right dual of a module are isomorphic if and only if S squared is an inner automorphism of the algebra. And let me indicate graphically how this looks like. I now write X for module or the underlying vector space. If we indicate write this like that, then for the right dual, we define the action is as follows. So we need to get a right dual. So we have to use the right duality. So we have X here, X dual here, and then this should be white. And then we know how to act on X, and we have a flip map. So we can act this way with, this should not be A, this should be H. If we do this, then actually this is not an action, but if we insert the antipode here, then it becomes an action. And that this gives you indeed a module is again a nice graphical exercise. So this is rigidity. Then we have to talk about pivotality. So there should hopefully be a corresponding notion for Hopf algebra, and there is. a pivotal Hopf algebra is a pair consisting of a Hopf algebra H and an element of H, which I call omega here, such that delta of omega equals omega tensor omega. One says that omega is group-like because this is the type of coproduct we have for the generators of a group algebra, and then secondly, the square of the antipode on any x in H can be written as omega times x times omega inverse. And then omega is called a pivot of the algebra. And then, as you would expect, otherwise one would not use this terminology. Mark or lemma or exercise, if H mod is pivotal. No, that is also a statement, but I want to start with if H is pivotal, then H mod is pivotal. Where, of course, the pivotal structure on the category is can be described in terms of the pivots, and conversely, if H mod is pivotal, then one gets a pivot on H, namely the I should not write it like that. I should write it like. Let me see. No. This is like what I'm actually so what we need is an element of H. This is the same. So what do we have from? So we pi goes from the identity to the double dual, and so we take the component of the pivotal structure at H, which is naturally an H module, and applied. We think of H as a vector space in the pi.
So pi H goes from H to H double dual. And then
Yes.
the inverse will be H double dual to H. And,
I have to look up what this. I have copied this from somewhere. Maybe I don't say more now. Another statement is that the group-like elements of H actually form group, which is also of some interest. And then Let me define one other type of structure for algebras that unfortunately I will not have time to use, most probably in any case, except for one statement that I will make. The left integral on a Hopf algebra H is a morphism from 1 to H, or an element of H, the same thing, such that, and I write this again not as a formula, but as graphically, if I take the identity times lambda and then the product, then this is the same as taking lambda after the co-unit. And analogously, a right co-integral of H is a morphism lambda from H to 1, such that we have a similar thing with co-product instead of product and unit instead of co-unit. And analogously, one defines left co-integral and right integral, but often one needs them in this order. And one notion you will see often is a unimodular of algebra. This is a Hopf algebra which has a left and integral that at the same time is a right. And then what I want to do with this, again, I'm getting a bit over time, but not as much as before, is that one defines the Frobenius map for Hopf algebra from H to H dual by taking the antipode, the product, and we assume that there is a right co-integral and that it's non-zero. Of course, lambda equals 0 would satisfy this property, but it's not interesting. And then we use the duality to get to H dual. And lemma, this is invertible with inverse given by, we assume that there is also a left, right co-integral and left integral that are both non-zero, and then we just use this in this form. And finally, an example, which is important in various applications and which uses a concept that we have introduced. So then we can use it. We take the co-end of the functor tensoring combined with duality in this way. This is an object in C if it exists, and let's assume that it exists. Then L has a natural structure of the Hopf algebra in C. And has left and right integral, co-integral, and Hopf pairing. And here I have made a step which I do not write out explicitly, I made all these definitions in vector spaces, but as I will explain quickly after the break, all of this generalizes to arbitrary monoidal categories once we introduce the structure of grading. And yeah, that's again 5 minutes right now. So I will have to finish in time this lecture, so I will speed up a little bit. Next subsection is about gradings. And of course, most of you know that. I have introduced the flip map and said that I can draw it like that, or flip. This is the same, but if we try to generalize this notion from vector spaces to arbitrary monoidal categories, then we get a situation where this is no longer true. So first we define now the if C is monoidal with tensor product with the usual notation, then we define the opposite tensor product. Let me see. As is just composed with, again, something I denote by tensor product composed with tau, where tau is where I say that X tensor opposite with V is simply the same as Y tensor with X, Y with X, and analogously for morphisms. And you can easily check that this provides, again, a tensor product. And then you call the same category, same underlying category, but with this tensor product and the same unit and appropriate associators and uniters. It's easy to describe what they are. They're just, maybe I write explicitly for the associator. The opposite associator has components U, V, W given by the associator W, V, U inverse. And similarly for the uniters that you call the category monoidally opposite to C. And then you say that a commutativity constraint on a monoidal category C is a monoidal isomorphism between the tensor product and the opposite tensor product. And I denote this by C. And then a grading on C is a commutativity constraint such that two so-called hexagon diagrams commute. And let me draw one of them. if we consider U tensor V, tensor W, and then take the associator with appropriate labels to change the bracketing, and then here apply the commutativity constraint for U and V tensor W, so that we get to V tensor W tensor U, and here apply it in the first two arguments tensored with the identity. Then we get to V tensor U tensor W, from which we can, again via the associator, get to V tensor U tensor W. And from both of these, we get to V tensor W tensor U here by an associator, and here by identity on V tensor with CUW. And we require that this computes, and here we start with a situation that we have tensor product of the first, and one can do something similar where one has a bracketing like that, where one has the opposite bracketing, but then again uses associator and C in such an order, but with other appropriate labels. And the two are independent. And you have to use, actually, if you draw arrows in the same direction, then they correspond to inverse. And then a braided monoidal category is a monoidal category with a braiding. Braiding is structure. So given monoidal category need not omit a braiding, and if it does, there can be several different ones. I mentioned already that two braided vector spaces, they have a braiding which is just a flip map inherited from vector spaces, and another one where I say that the odd unit, so k 0, 1, breaks with itself with a minus sign. And then we have taken explicitly here the associators. If we have a strict category, then these are identities, so the hexagons just look like triangles. And it's easy to see that if C is a braiding, then C bar defined by C bar UV being the VU component of the inverse of C is also a braiding. And then there is a scatter case which I don't write down. If it turns out that the braiding is equal to the inverse braiding for all pairs of objects, and say the category is symmetric or has a symmetric braiding. So the flip map that we use for vector spaces makes the category vector spaces into a symmetric monoid. And graphically, finally, I use what I used before, so C, X, Y. I go like this, and then this means that this other picture is actually CYX inverse, if I use the same X and Y here. And then the hexagon identity, for example, looks as follows. U V tensor W, braid by saying that I first take the braiding with U and V times the identity on W, and then the other way around. Of course, in the diagrammatic description, you don't see the associated.
Excuse me. The tensor function, the tensor product is not a tensor function.
It's not, no. Let me see. No.
So, let
me see. No, it has. I'm not sure.
Yeah, natural. Just naturalizable. As functors in C.
Yes,
Cross C to C.
Yes.
These two functors are isomorphic as functors.
There's no much. No, I didn't. Now, once I have a braiding, and I don't have to write anything about it. If you take the definitions of commutative algebra, co-commutative algebra, of bi-algebra, of Hopf algebra, of integral and co-integral, and Hopf pairing involves that automatically generalizes. But if we suitably replace slip maps by gradings, then all those definitions make sense and arbitrary monoid. You have to be careful if you if in a given formula you have more than one grading, then you have to do this in the proper way. If you erroneously exchange, or for example, in the definition of Hopf algebra, I still require this property. If I would use the inverse grading here, then I would not get a Hopf algebra. I would, I think, get a bi-algebra with two algebra. That's not what one typically wants. So once we have graded categories, then there will be a corresponding notion of functor, a graded monoidal functor between graded monoidal category C and D is a monoidal functor f by 0 by 2, such that the following diagram commutes. If I take a tensor product of f of x and f of y, I can use the monoid structure to get to f of x tensor y. So this is the xy component here. I can use the grading to get to f of y tensor f of x, and I can take the other component of phi2 to get of the f of y tensor x, and then I can take so this is a braiding in D then, of course, and here I can take f of the braiding in C to get here, and this diagram should come. And if the categories are symmetric monoidal, then we call this symmetric monoidal. And braided monoidal transformation is nothing else than monoidal transformation. How is this related now to Hopf algebras in the case of vector spaces? I have to do this briefly. There is a notion of a quasi co-commutative by algebra. This is a by algebra, let's say H, together with an element in the tensor product, such that the opposite, co-opposite co-product and the ordinary co-product are related in this way by if R should be invertible, we can bring one of the R's to the other side, and then this is conjugation by R. And if you have if this is even a Hopf algebra, you call it a quasi co-commutative Hopf algebra, and then a quasi triangular Hopf algebra. Is a quasi co-commutative Hopf algebra, where in addition you have delta tensor with the identity applied to R equals R13 times R23, and the second equation of the same type, where this means the following. This is an equality in a triple tensor product of H. Here it's clear you apply the identity to the second factor and delta to the first, and this means that you take in Sweetler notation, you would take R1 and then the identity in the second element and R2 in the second factor, and R2 in the third factor. This would be R13. And analogously for R23. And then the statement is that there is H mod, which we have seen as a monoidal category, where H of algebra is braided if and only if H is quasi-triangular. And actually the proof is, when you prove this, this is constructive. So given a braiding on H mod, you can define an R matrix. And given an R matrix, you can get a braiding. That's easy. It's like follows. You take the flip map. R matrix is an element in H times H, so you can regard this as a morphism from the field. So two copies of H, and with one of them you act here, and with the other. And in this case, its relevancy is the correct way. I have to say a few words about the Drinfeld center of a category, and this in itself could easily be a whole lecture. So this is just some very basic aspects. Definition. We have I take A to be a monoidal category. And then we say a half braiding on an object X in A is a natural family of isomorphisms let's call it gamma. So gamma gamma y from y tensor x to x tensor y, such that, and now I require one of the two hexagons, and let me just draw it first. So we take y prime, and x, and here we take y tensor y prime and x again. And if we had a braiding, then this would be one of the braiding axioms. But now we say here we have gamma for y tensor y prime, and here we have gamma y and gamma y prime. So probably one should introduce a separate symbol here, but since I will not use this explicitly, I don't do it now. And then the Drinfeld center. Set of A of the monoidal category A is the category with objects being pairs of objects of A and half braidings on X on that object, and morphisms being, maybe I continue here. Let me just also do it graphically. These are those morphisms from X to X prime, such that for any Y, if I have gamma Y, so here the object in the Drinfeld center is X gamma, that this is the same as if I first go to X prime and then use gamma prime Y here. And it's easy to see that the Drinfeld center always is graded. The grading is, in a sense, defined by just using the other the analog of the other hexagon. And let me just mention that as last statement that the definition is fine, but it doesn't really help you to tell what the Drinfeld center of a given category is, because finding half ratings might be very hard. But there's one exception, This is if H is if A is H mod, then Z of H is D of H mod, where D of H is called the Dirichlet double of H. This is a Hopf algebra which, as a vector space, is the tensor product of H with its dual. And finally, one thing particularly interesting is the case that you have a category C, which is braided monoidal equivalent to C box times C bar. This is the linear product that we have mentioned, and C bar is C with the opposite braiding, which are fancy from. So there is one further structure besides rigid structure and grading on the monoidal category that is important and which can be combined with the others in order to make categories with this property particularly interesting, and is what is called a written structure. I don't write numbers now to save some time. Written category is a monoidal category with grading, rigid graded monoidal category. Together with twist. Sometimes this is also called the balancing or ribbon twist. And this is a natural family of automorphisms, invertible endomorphisms for all x and c, such that this is in the following way compatible with braiding and residuality. Let me denote this component theta x by this symbol here. Then we have that we can, so to say, take the twist through co-evaluation, and in the same way through an evaluation, and then concerning the braiding, if we take a tensor product, or concerning tensor product, one could say is that a twist on tensor product is the same as the twist separately on the factors, and then a double braiding. And actually, it's enough to require that this is a one-sided rigid structure. I have used only right duality here. One could do the same with left, and the reason for that is the following result. If a category is ribbon, then it's two-sided rigid. Namely, one can define left evaluation and co-evaluations in terms of the right one, and twist and grading like that. If I add right co-evaluation here, twist, grading, and the twist here, then I get something which behaves like left co-evaluation, and for the evaluations it's analogous, except that you have to be careful with the with the braiding. If it's an over braiding here, then it's an under braiding. By the way, it follows from these properties, in particular that for the monoidal units, the twist is trivial, and the twist of the dual of an object is the same as the dual of the twist. You could ask what whether you can get a twist from a braided category that is also pivotal. It turns out there are actually two ways to do that. Let me just, instead of describing them, refer to a paper by Henriquez, Pennies, and Wiener. But the opposite direction, that's easier. If you see that if C is written, then it is in particular pivotal. And you can just define the pivotal structure like that. So here we have the twist, and here we have explicitly braiding and duality. And you see this goes from X to X. Then we have X dual here, and here we have yeah, X double dual. And in fact, the so obtained pivotal structure is always already certain. And then finally, in the last 5 minutes, or maybe 6, let me say something about finite tensor categories. And I will not finish all that I wanted to do. Maybe I add a little bit tomorrow. We have introduced the notion of a finite category before. So a finite tensor category is a monoidal category, is a rigid monoidal category which is finite. Almost, at least. If you have this, this is called a finite. This is called a finite multi-tensor category. If it's finite, if one is linear simple. No one, yeah. Let me be on the safe side and say simple and linear simple, which is equivalent. They are equivalent if the field is nice enough. And then a finite Ripon category is where, in addition, you have a Ripon structure, and there's a notion of fusion category. This is a semi-simple finite tensor category. Historically, many results have been obtained for fusion categories, and it then has been seen later that they generalize in a natural way to non-semi-simple finite tensor categories. So examples: if H is a finite dimensional algebra or a field, then the finite dimension, then the category of H modules is a finite tensor category. And if H is also semi-simple, then it's a different category. And if H is a triangular, then it's a grade finite tensor. And then finally, now I think I can take up most of the things that I wanted. The definition: a transparent object in a generally in a braided category. This is an object X such that, let me just do it graphically. The double braiding, so CYX after CXY is the same as the identity for all Y and Z. And we say that braiding C is non-degenerate. If and only if the only transparent objects are direct sums of the tensor unit. Finite direct sums. And then finally, modular tensor category. Often abbreviated as MTC, is a finite ribbon category with not a general braiding. And the modular fusion category often abbreviated MFC is the same and in addition semi-simple. And I write this out in particular also for historical reasons. Until maybe a decade or so, ago or so, when one said modular tensor category, one usually meant semi-simple, but the terminology has fortunately shifted. When one says modular tensor category, one means finite, and not necessarily semi-simple. And Mark, there are several interesting equivalent characterizations of modular, and I refer to a paper by Shimizu on where you find details on that. First is that, as I wrote before, we have this braided equivalence between the center and this linear product. To be precise, it's not just that this is braided equivalent, but a certain functor gives us a braided equivalence, namely the functor in this direction here, which sends an object of the specific form x box times y to their tensor product, together with we have to specify a half grading, and the half grading is as follows. C by assumption is braided, so they have a braiding, and then gamma z is as follows. So we have to say what a half grading with z is for sorry, now I let me see. It should be no. I probably, this is what I have drawn, but I have defined the half in the literature. The half grading is sometimes defined with the object on the right and on the left. So I have it on the left, so I have x and y here, and now z here, and then it should look like this. But this is the braiding. So, and I had written it in my notes the other way around because I have switched to the other convention, which I have not used in the document. And so this is one characterization. And then the second one, there is a third and a fourth, which I do not give. Remember this coend. Which exists under certain conditions, and it exists in particular for finite tensor categories, finite Ripken categories. I have already said this is a Hopf algebra, has a integral and co-integral and a Hopf pairing, and here one requires that the Hopf pairing is non-degenerate, meaning that if you take the Hopf pairing and combine it with a duality, then this gives you an isomorphism. And then a final few minutes for the following. To explain the terminology modular. We have a Ripken fusion category. So finite tensor category in semi-simple and Ripken. Then define numbers as lambda mu. So these are labels in this set of isomorphism classes. Simple objects are given by the trace of the double braiding of y lambda with y mu. And this is in particular circle, so left trace is equal to right trace, and T lambda mu is delta lambda mu times theta lambda, where theta lambda is defined by saying that the twist on y lambda is the number theta lambda times the identity. Has to be a multiple of the identity because in this situation these are simple and linear simple, and then it follows that C is modular if and only if S is invertible. And also in this case, S tilde and T, where S tilde is a certain multiple of S, which I do not want to specify, generate representation of the group SL2Z, which is also called the modular group. The mapping class PSL of 2Z is the mapping class group, which is called the modular group. And now I have to stop. With my Zoom, which I have to do.